we have an Agilent GCMS. So I'm going to start out describing the gas chromatography portion of the instrument, and we'll end up talking about mass spectrometer. So first of all, for our GC, one of the things we need is a mobile phase or a carrier gas. This right here is our high purity helium. That's the carrier gas for our gas chromatography system. And it's hooked up to some gas filters right there. One of those deals with moisture and the other eliminates oxygen, both of which can decompose our gas chromatography column. And then as we move over to here, we can actually see where our heated injector, let's get a little closer look at that. So that's our heated injector port. So this is held to a high temperature. A needle is actually permeated down in there and it actually goes through a septum. I'll show you what this looks like from the inside. There's our little rubber septum that covers the entryway. And again, that rubber septum keeps it sealed once we actually remove the syringe. Obviously this isn't heated right now, but typically it's held at over 200 degrees so that you can actually vaporize your sample as soon as it is injected. We have a front injector as well. It's beneath this auto sampler. So the auto sampler obviously is used to inject our sample consistently. So we have an auto injector. We have our syringe up in there. And of course we can load up to 16 samples into our little auto sampler right here. There is lots of versatile different auto samplers that hold more than that, but 16 seems to do it for us. So once we are injected, vaporized, we enter the oven. Of course, the oven is where we actually have our separator columns. So our inlet ports are over here. We have two columns. The back column is actually the one that is hooked up to our mass spectrometer. The front column is actually hooked up to our flame ionization detector. So these are both 30-meter columns. They're very similar. They're both non-polar 5% polysiloxane columns. Pretty typical. So again, injector over here. Up here, this column is actually hooked up to the FID, flame ionization detector. And then over here is our transfer line that takes us from the GC, so our capillary comes right in here, and it passes through. This is a heated line, it's about 280 degrees, and it passes into our electron impact source, which is where our sample gets ionized. So I mentioned we have a second detector. That's a flame ionization detector. This is the actual flame ionization detector. And so what happens here is that a hydrogen flame is actually produced in here. Our hydrogen and air are over there. So we have hydrogen as the fuel and air as the oxidant. So those are fed in here. And we have a tiny little cone on the inside, which you can't really see, but we have a tiny little cone on the inside where our sample comes up from, as it leaves the column, it enters our flame ionization detector where it's combusted and it's actually converted into ions. So the carbon in particular of our samples is converted into ions, and those ions then can be detected as a current that actually passes. And so the more carbon the the analyte contains, the larger signal it actually produces. Other than that, it is completely dependent on concentration. But it's a mass-dependent detector. So as the column leaves, our ultimate detector here is our mass spectrometer detector. So as our sample exits the column, it actually passes into this electron impact ionization chamber, and it is operational right now because I'm running a tune, which is why it's blowing. So our sample comes in through that transfer line off to the right, passes into the extraction lens, or the ionization lens. So it's the electrons hit it. It's 70 EV electrons, bombard it. They end up ionizing the samples, and it ends up being fragmented. And so the fragmentation patterns are unique to the structure of the molecules, and so it can be used for identification. And of course, the intensity of the ion fragments have to do with the concentration of the samples, just as for most chromatography samples. Okay, so once ionized, the ions the ion fragments are accelerated into the mass spectrometer. It's behind these electronics here under high vacuum. So our vacuum system consists of a roughing pump that actually comes in where the inlet port is, over near the ionization, over near the ionization source. And then of course we have a diffusion pump down under here that's down below. So the diffusion pump brings us down to a high vacuum, which is required when you're doing mass spectrometric separations, because the ions are accelerated through the quadrupole mass spectrometer, and those that have an unsteady trajectory will annihilate on the poles, and those that have a steady trajectory will actually make it through to the electron multiplier that's attached to the back of the mass spectrometer. That's our detector and amplifier for ions exiting the mass spectrometer.